This film will show the principles governing the operation of DC motors and generators. Basic to the understanding of DC motors and generators is the simple generation of an electromotive force, an EMF. Mechanical energy, the moving of a wire or conductor across a magnetic field by hand in this instance, produces electrical energy. The magnetic field is composed of lines of force. As the conductor cuts these lines, an electromotive force, or EMF, is generated in the conductor. Moving the conductor down through the field makes the needle of a voltmeter deflect one way, which means the EMF has one direction. Moving the conductor up through the field produces the opposite deflection of the needle. The EMF has now changed direction. Moving the conductor back and forth with the field does not make the needle of the voltmeter deflect. There is no EMF because the conductor is not cutting the field. To illustrate the direction of current flow, the conventional symbols will be used. Current flowing in a conductor away from us is represented by a cross, toward us by a dot. However, moving a conductor in and out of the field in this straight reciprocal fashion is awkward and impractical. A simple generator of EMF can also be made by rotating a single turn coil within a stationary magnetic field of two magnets with opposite polarity. The loop now, in effect, becomes two conductors, because both the top and bottom sections cut magnetic lines during rotation. Since they cut lines of force of opposite directions as they rotate, EMFs of opposite polarity will be generated in the conductors. In order to have current flow in this circuit, polarities of the two conductors must be opposite. The amount of EMF generated at any instant is determined by three factors: the strength of the magnetic field, that is, the number of lines of force, the length of the conductor cutting the lines of force, and the velocity with which the conductor is turning. We can determine the amount of instantaneous EMF by a simple formula. The instantaneous EMF E equals B, the strength of the field, times L, the length of the conductor cutting lines of force, times V, the velocity of the conductor. An increase in the number of lines of force, or the strength of the field, increases the instantaneous EMF in the conductor. Increases in the length of the conductor cutting lines also increases the EMF. And finally, the greater the velocity of the conductor, the greater the EMF.